This video is brought to you by mywayteaching.com.
So, in this particular part, we are going to study thermodynamic processes. And that the first part is quasi-static process. Okay, you consider a gas in thermal as well as in mechanical equilibrium with its surroundings. Okay, thermal as well as in mechanical equilibrium. The pressure of the gas in that case equals the external pressure, and even its temperature is same as that of its surroundings, isn't it? Suppose that the external pressure is suddenly reduced, say by lifting the weight on the movable piston in the container. The piston will accelerate outward. During that process, the gas passes through the states that are not equilibrium states. The non-equilibrium states do not have that well-defined temperature and pressure. They'll be not having that uniform temperature and pressure. In the same way, if a finite temperature difference also if it exists between the gas and its surroundings, there will be a rapid exchange of heat during which the gas will pass through non-equilibrium states. So in that case, the gas will settle to an equilibrium state with well defined temperature and pressure which is equal to that of the surroundings. Okay, the free expansion of a gas in vacuum and a mixture of gases undergoing an explosive chemical reaction are all the examples where the system goes through non equilibrium states. Okay, in the middle the system may go through the non equilibrium no states. In that particular case, the heat exchange with with the surroundings may takes place, because when it will come to a non equilibrium state, again it will try to maintain that uniform temperature and pressure, isn't it? So the free expansion of a gas you can take as an example in vacuum, and a mixture of gases undergoing an explosive chemical reaction. Okay, these are all the examples where systems goes through non-equilibrium states. See, the non-equilibrium states of a system are difficult to deal with. It is therefore convenient to imagine an idealized process in which at every stage the system is in equilibrium state. Such a process is in principle infinitely slow, and hence the name quasi static, which means it is nearly static. The system changes its variables, that is, that the variables pressure, temperature, volume so slowly that it remains in thermal and mechanical equilibrium with its surroundings throughout. So, in this quasi-static process. At every stage, the difference in the pressure of the system and the external pressure is really small. The same is true in case of temperature difference between the system and its surroundings. To take a gas from the state, okay, we are considering a gas which is having the P, temperature T, and pressure P and temperature T. Okay, and we wanted to change it to the another state where it becomes P dash and T dash via quasi-static process. Okay, so we change the external pressure by a very small amount, allow the system to equalize its pressure with that of the surroundings, and you just continue the process infinitely slowly until that system achieves the pressure P dash. Similarly, you do with the temperature. You just change the temperature, then we introduce an infinitely small temperature difference between the system and the surrounding reservoirs. And by choosing reservoirs of progressively different temperatures, T to T dash, the system achieves the temperature T dash. Okay. You can see in a quasi-static process, the temperature of the surrounding reservoir and the external pressure differ only infinitely small from the temperature and pressure of the system. See, a quasi-static process is obviously a hypothetical construct because in practice processes that are sufficiently slow and do not involve accelerated motion of the piston, large temperature gradient, etc., are reasonably approximation to an ideal quasi static process, except when stated otherwise. So a process in which the temperature of the system is kept fixed throughout is called an isothermal process. Okay, we call the process as an isothermal process only when its temperature is fixed throughout the experiment. Okay, the expansion of a gas in a metallic cylinder placed in a large reservoir of fixed temperature. This is the example for an isothermal process. Okay. Heat transferred from the reservoir to the system does not materially affect the temperature of the reservoir. because of its very large heat capacity. Okay, in isobaric process, as the name itself tells, what is constant? Yes, in isobaric processes, the pressure is constant. In isochoric processes, volume is constant. Finally, if the system is insulated from the surroundings and if no heat flows between the system and surroundings, then we call those kind of processes as adiabatic. Okay, when system is insulated from the surrounding and when no heat flows between the system and surrounding, we call those kind of processes as adiabatic process. Okay, so here in this particular table it gives some special thermodynamic processes. So we have already discussed this. In isothermal, temperature is constant. In isobaric, pressure is constant. In isochoric, volume is constant. And in adiabatic processes, no heat flow between the system and surrounding, which means delta Q is equal to 0. Okay. So now let us study about isothermal process. See, for an isothermal process, temperature is constant. We all know that. So, the ideal gas equation gives PV is equal to constant. So, the pressure of a given mass of gas varies inversely as its volume. This is nothing but Boyle's law. Pressure varies inversely with the volume. Suppose an ideal gas goes isothermally from its initial state, that is P1 V1, to final state, that is P2 V2. At any intermediate stage with the pressure P and volume change from V to delta V plus delta V, we know this delta W is equal to P into delta V. So taking delta V tends to 0 and they summing the quantity delta W over the entire process, we get W is equal to V1 to V2 PdV. Is that fine? Yes. In that particular case, it will give the equation mu RT dV by V, that is mu RT plus mu RT ln of V2 by V1. So where in this second step we have made use of ideal gas equation, that is PV is equal to mu RT. This is the ideal gas equation, isn't it? And here we have taken the constants out of the integral. For an ideal gas, internal energy depends only on temperature. So, thus, there is no change in the internal energy of an ideal gas in an isothermal process. Okay. The first law of thermodynamics then implies that heat supplied to the gas equals the work done by the gas. We know it from the first law of thermodynamics. Heat supplied to the yes, supplied to the gas is equal to the work done by the gas. So, for V2 greater than V1, W greater than 0, and for V2 less than V1, W less than 0, that is, in an isothermal expansion, the gas absorbs heat and does work, while in an isothermal compression, work is done on the gas by the environment, and in that particular case, heat is released.